Hello everyone, today I will talk about historic paper and environment. My research was about investigating the relationship between the agents of change, specifically the environment, and the materials, which in the case of archival collections are historic papers. And this helped the development of the dose-response function, which is where basically my research fits into the collection's demography model. So now let's start
with environmental effects on paper degradation. These are, of course, temperature and relative humidity, which Mattia talked about extensively already. And there are also pollutants, which we should or should not take into account. They are composed of outdoor-generated pollutants, such as nitrogen dioxide, sulfur dioxide, particulate matter, which come into the collection from outside. And the second ones are indoor-generated pollutants, which are VOCs, that are generated by the collection itself. So they're nicely being emitted from the books and from the boxes. And this makes them problematic because basically they're very difficult to get rid of. To start with temperature and RH monitoring, this is monitoring that was carried out in two different repositories in the National Archives of the Netherlands. You can see both of the plots look quite messy and quite scattered, but basically temperature only deviates by plus minus 1 degree, and the same for the other repository here. And this is a yearly plot, so that's why it looks quite spiky and the fluctuations seem extensive, but they're actually not as bad as they might seem. The RH in one of the repositories only fluctuated by roughly plus minus 2%, and in the other one a bit more, but generally the worst case scenario was plus minus 10% RH. And to investigate how this affects paper degradation, we carried out experiments, and basically we did experiments at the cycling temperature and the steady state RH, and the cycling RH and the steady state temperature. The fluctuations were in a realistic kind of range, which is a temperature fluctuation of plus minus 5 degrees and an RH fluctuation of plus minus 10%. And they were compared to degradation rate at kind of median temperature and RH conditions. And as you can see here on this graph, on this axis we've got degradation rate at cycling conditions, and on this axis there are degradation rates at constant conditions. And let me just point out that experiments here were carried out on real historic papers as well, in addition to a few model papers. And you can see that the rates are in pretty good agreement with each other, which basically means that there is no significant effect of temperature and RH fluctuations in fairly reasonable or kind of mild fluctuation range. To carry on from that, we should probably talk about pollution. Since basically we haven't discussed pollution yet, and it's been quite a big topic over the past few years, and we still haven't quite decided whether pollution actually matters or not. Pollution, as I mentioned already, is composed of outdoor-generated pollutants and indoor-generated pollutants, and indoor-generated pollutants attracted quite a lot of attention in the recent years, especially acetic acid was quite a big topic. And generally, the risk of pollutant-induced degradation is assessed using pollutant doses. Now, the pollutant doses are generally being used quite a lot and we're still not entirely sure, at least I wasn't entirely sure, whether this concept is actually appropriate for studying paper degradation. So now to just explore the concept a little bit, this is a pollutant dose derived from toxicology studies. And as you can see in the top line, pollutant dose is actually a fairly complex term, because the total accumulated dose here, AD, is composed of initial accumulated dose, of intake dose, which is what's being absorbed, for example, by an object or by an organism in toxicology, and with eliminated dose as well, which is composed of emitted and produced dose. Produced and emitted dose, basically, the difference between the two is that one is a physical process of desorption of pollutants, for example, from a book, and the second, produced dose, is basically a chemical process where cellulose chains break down and short fragments of chains break off, which then form volatile organic compounds. So basically, these two processes are completely different, but experimentally they're extremely difficult to differentiate. Which basically leads us to the fact that all of these different doses, which should probably be taken into account if we want to talk about pollutant doses accurately, are actually extremely difficult to determine. Which makes us think that maybe concentrations and exposure times are much more practical and much easier to operate with. And this is why concentrations and exposure times, I assume, are being used quite widely. But what we tend to forget about when talking about concentrations and exposure times quite a lot are the assumptions that we're actually subconsciously making when talking about that. And the first, and in my opinion, the most important assumption here is that the pollutant damage or pollutant-induced degradation is significantly more important than the effects of temperature or RH, of light, or of any other kind of paper degradation effect. The second assumption which is used here is the reciprocity principle, which basically says that pollutant concentration multiplied by time is a constant, and which is where the whole 100 years at 10 ppbs equals 10 years at 100 ppbs. That's where this principle comes from. Do these assumptions actually hold? Well, that's a pretty interesting question because it can't be generalized to all materials and all pollutants. It basically depends on specific pollutant-material interactions. And in some cases, yes, the pollutant effect can absolutely be prioritized, for example, in silver tarnishing, which is not really affected by temperature very much. But it does not hold for all pollutant-material interactions. One such example would, unfortunately, be paper degradation in a realistic archival environment. Linearity or the reciprocity principle could also be problematic, possibly at very high pollutant concentrations, because we're not entirely sure whether the actual chemical mechanism of the degradation process is the same at very low pollutant concentrations and at very high pollutant concentrations, which are commonly used when carrying out experiments. And for paper degradation specifically, which is the main topic, which was the main topic of my research, pollutant effect is actually comparable, or in some cases even much smaller than the effects of temperature and relative humidity. Specifically for, especially for acetic acid, it was found that the effects of temperature and RH are much more pronounced in comparison to kind of realistic concentrations of acetic acid. So basically this means that all these different effects have to be taken into account when we're talking about paper lifetimes. So let's just kind of a recap on pollutant doses. This is the traditional dose approach. Concentration multiplied by time is a constant, which gives us the very famous kind of equal relationship here. And what happens here is that when experiments are carried out at very high pollutant concentrations, the interpolation to realistic pollutant concentration is carried out between 0, so no degradation at all, and the degradation that was obtained at this specific pollutant concentration. And the slightly different approach that we're introducing here says that not the concentration, but the degradation rate multiplied by time is a constant, as you can see here, which means that this is not equal anymore, because in 100 years, a lot more degradation will happen just because of the effect of the temperature and RH and all different factors than there would in 10 years. And here, interpolation of experimental results was carried out between the degradation rate obtained at a certain temperature and RH, and the degradation rate obtained at the same temperature and RH and an elevated pollutant concentration. So basically, what we're doing here is taking into account the so-called background degradation that is led by temperature and relative humidity. And significant differences between these two approaches can be expected when pollutant concentrations are low, which means that in comparison, temperature and RH are significant. And when we're talking about pollutants that are not as damaging as in some other instances. Basically, here we've got predicted predicted lifetimes of paper. This specifically is acidic paper. And in black you can see the traditional approach, which is concentration multiplied by time, and you can see fairly long lifetimes. And in pink you can see the new approach introduced here. And as you can see from the graph, the only overlap between the two predictions is at a very high concentration of a pollutant, which is very damaging to paper. In cases of not so damaging pollutants, such as acetic acid here, the differences are significant. And even in the case of NO2 at a lower concentration, which is actually, this is a realistic concentration in an archival repository, there is quite a significant difference between the two predictions. The same happens with display lifetimes. Again, quite a good overlay of the two for a high concentration of NO2, but otherwise pretty big differences. And basically the danger in using this approach, the traditional approach, is that we would significantly overestimate lifetimes at low pollutant concentrations. Because you say, okay, at 10 ppm, this is going to last for 1,000 years, and you're actually not taking into account the fact that in 1,000 years, temperature and RH are going to do its bit towards degradation. And this basically leads us to pollutant thresholds. I think we're all probably interested in hearing what a safe pollutant threshold or what a sensible pollutant threshold is when trying to control the environment. And basically here we took two different approaches to defining pollutant thresholds. The first approach presented here is that a pollutant threshold is a concentration of a pollutant at which the effect of the pollutant or the contribution of the pollutant towards the degradation rate becomes significant. And significant here was defined as being larger than the uncertainty in the control of temperature and RH. Because basically, the question here was whether it makes sense to try and keep the pollution out if we're not entirely sure we're keeping the temperature and the RH at these decided levels, and this might actually contribute more to the degradation process. And here you can see the thresholds for acetic acid. Here this is display and handling, and for NO2. And generally most thresholds are kind of in the realistic concentration range, because generally a rough estimation is that in a normal archival repository you could find approximately 10 ppbs of NO2 and approximately 100 ppbs of acetic acid. And generally it's in that kind of area, although NO2 in some cases is a bit lower, and acetic acid is as well. And you might want to keep in mind the rag paper, which has actually very, very low thresholds, but I will discuss this later on. So now let's go to the second approach to defining pollutant thresholds, which was by using the acceptable lifetime that Kath already talked about and Mattia in the previous presentation. And here we decided on we gathered that 500 years was an acceptable lifetime, and basically I then calculated pollutant concentrations which would still allow the papers to reach the lifetime of 500 years at 80 degrees and 50% RH, which are the conditions at the National Archives of the Netherlands, who I was working with. And I forgot to mention this in the previous slide, I'm sorry. These are 5 different paper types that I calculated this for. It's acidic, neutral, alkaline, rag, and lignin-containing paper. And these were really historic papers that I did all of my experiments on. And here you can see that if we take the lifetime of 500 years into account, all the thresholds go up significantly. And generally everything you can see in this table is higher than realistic pollutant concentrations, at least in the so-called Western world or in the post-industrial cities. This would definitely be above realistic pollutant concentrations, which in a way says, okay, pollutants as we know them are quite okay. It shouldn't be a big concern, except for where you can see the little stars. The little stars mean that this paper would not reach a lifetime of 500 years, even at only 50% RH and 18 degrees with no pollution. So basically, just tackling the pollution problem in this case wouldn't help bring the paper to this acceptable lifetime. So maybe we should probably control some other factors as well. This kind of leads us to different preservation measures which were compared here. I did experiments on the papers that I just described, and here I'm just going to talk about acidic paper and rag paper. Those, as I said, are both really historic papers. Here you can see the initial pH values, but quite significantly different initial DP values. And the preservation measures I compared here are a temperature decrease of 2 degrees, an RH decrease of 5%, and air filtration. Air filtration data is data I obtained by monitoring the 2 repositories in the Dutch National Archives. And basically one repository has air filtration and the other doesn't. And this is a comparison of the 2 concentrations I measured over there. And the first graph here is for acidic paper. The black squares are the kind of starting point. So 80 degrees, 50% RH, and no air filtration. And then the red circles are an RH decrease. The pink triangles are a temperature decrease, and the blue triangles are air filtration. And here you can see that for acidic paper, actually air filtration would have more effect than decreasing the temperature by, let's say, 2 degrees. However, this doesn't mean that air filtration is always much better than controlling other environmental parameters, because if we would decrease the temperature by a bit more than 2 degrees, we could achieve the same result. And the temperature which would be kind of comparable to the effect of air filtration is approximately 4 degrees, at least for acidic paper. The second paper here is rag paper. Again, the same symbols as in the previous slide. And you can see basically that all different kind of preservation measures are quite clustered together, which basically means that it looks like nothing would make very much sense for rag paper except air filtration, which has a massive effect. But what we should really carefully look at here is the starting lifetime that we're starting with, which is several millennia. This is roughly 6,000 years. So if you think that 6,000 years is still not enough and maybe we need 20 or 40, then yes, air filtration is very necessary. I mean, this is obviously not my decision, but it's yours. But it's just kind of to give you a rough idea that yes, air filtration would make a difference, but we just have to decide on what we think is acceptable for us. And on that note, I'm going to finish this presentation. Basically, the findings of my research were used in the development of the general dose response function, and hopefully we made some useful contribution to redefinition of pollutant thresholds, and hopefully this could be used as recommendations for environmental management. And in the end, I would just like to thank the National Archives of the Netherlands, and especially Gabriele and René over there for all of their help. And thank you very much for your attention.